Okay, so now we'll pick up the conversation on designing a piece of hardware for the ALU, the arithmetic, the part of the processor that does math. And so far we've talked about where we can add numbers. We have a ripple adder. And then if we can add numbers, we can subtract numbers because we can store them as 2's complement and then add the negative of a number. So, and we also talked about how we can shift a number over to multiply it by 2 or shift it to the left. We shift it to what? We shift it to the left. No, shift it to the right, it divides by 2, shift to the left, multiplies by 2. But what if we wanted to multiply bigger numbers? So this is more of like a theoretical talk on it, how we would design a piece of hardware that can multiply numbers. But it might be a good idea just to go over how we multiply in general. So suppose we had decimal numbers, decimal number like 214 times 21. So the way you learned this when you were a kid was you would take, decide one of these numbers is going to be multiplied by the other number. So we would take this number and say, okay, the lowest column is a 1, so we'd multiply 1 times the entire top number, and we'd write 214. 1 times 214 is 214. Then we slide over a column because this 2 is really a 20, so it's 10 times 2. So really we're going to multiply this number by 20. So we put a 0 here, and then multiply 2 times 148 gives us 2 times 214 is 428 with a 0 added. And then we're going to add this number to this number and make a total out of it. So the total will be 4,494, right? Okay. Another way of thinking of it, if you wanted to write the number in scientific notation, so scientific notation is where you write the entire number multiplied by some base raised to a power. So another way of thinking of the number 214 is 2.14 times 10 raised to the 2 power, times 100. Another way of thinking of 21 is 2.1 times 10 raised to the 1 power. If we wanted to multiply the numbers in scientific notation, we would multiply this part times this part, which is really going to be just as much work as doing this, right? All we're really doing is putting in decimal places in front of the most, right after the most significant digit. So the amount of work would be the same, but then as far as the exponents, we would just add the exponents together to get the next number. So we would end up getting 4.494 times 10 to the 3rd. So 2 different ways of multiplying numbers, whether using scientific notation or not. If you wanted to do the same thing in binary, it's the same operation. We would have a number, let's say for example this is 11, so these are unsigned numbers, they're not positive or negative, just 4 bits to kind of make the point. If we wanted to multiply 11 times 14, and we're doing it here in decimal just so you can follow along, what we'll do is we're going to say 0 times this number, and write that here. Then we're going to put a 0, we're going to start sliding it over. And I left out the zeros because I'm just showing how we're just sliding the computation over by 1. Anytime there's a 1 here, we're going to multiply 1 times this number, which just means repeat the number. We don't have to actually do any multiplication, we're just taking the number and writing it here. And if there's a 1 here, we take this number again and write it here. If there's a 1 here, we take these 4 bits and write them again here. And then just add these all up. Same way we're doing it, if you were doing it on a blackboard, not doing it on a computer, just writing it out on a blackboard, you might do something like this. As opposed to here, we'd say 4 times 11 is 44. 1 times, then we'd slide up, put a 0 here. 1 times 11 is 11, then add this up and get 154. Okay, but it's a lot easier in that, so for example, when we said 4 times 11, we had to actually do a multiplication to get the 44. In this case, we're either doing 0 times this number or 1 times this number. If we're doing 0, we don't actually do anything. We can almost skip that step. And if we're doing a 1, we don't actually do any multiplication, we just copy the number. So if we had a register that contain these 4 bits, we could just keep sliding it. Every time we slide, we AND it with this bit, and if it's a 1, we add the previous number to this number, and if it's a 0, we just put it to an AND gate and it'll 0 it out. We don't even have to add it. So this operation can actually be done somewhat quickly. What we're really doing is we're taking this number and we keep adding it to itself, 1 bit slid over if the bit here is 1. And if it's a 0, don't even do this step. Okay. So yeah, a little bit of history is until the late 70s, processors never had a multiplying piece of equipment that if you wanted to multiply 2 numbers together, you would have software that would take one of the numbers, put it into an accumulator, a register that started off at 0, and just keep adding the number to itself with the number shifted over. So you would be running basically a mini program that adds the number over and over. And the worst case scenario, if you're multiplying 2 32-bit numbers together, is you may have to run the loop 32 times. Actually, if it's a 32-bit signed number, the last number is assigned, so it would be 31 times in the worst case. But then as transistors got cheaper and cheaper, the idea of making a piece of hardware that could do this faster started to become interesting. So, for example, this is just if we had 2-bit numbers, right? So here's a number with 2 bits. So it could either be 0, 1, 2, or 3, right? Because it's only 2 bits. 2 bits times a 2-bit number. So what's the highest possible result if these were unsigned numbers, if these were no negative numbers? So the smallest number would be 0 times 0 is 0. The smallest result would be 0. What's the highest result? 9, right. So, yeah, like I said, this is a small example. As the examples get bigger and bigger, they'll get a little bit more chaotic. But yeah, so the highest thing we could go to is 9. Now we need 4 bits to capture a 9. Okay. So if we just did the logic on what would make the lowest bit come out, what would make this turn on? If you multiply 2 unsigned numbers together, what would cause the lowest bit to turn on? It would turn on if it was an odd number, right? Only if it's an odd number we would turn this thing on. So what would have to happen for the what would the 2 inputs have to be so that the result is odd? They would both have to be odd, right? If you multiply 2 even numbers, you get an even number. Actually, if you multiply 1 odd against 1 even that's even, right? So the only way to get an odd result would be if the 2 inputs were odd, right? So this bit, the lowest bit, and this bit would both have to be on, right? So if you look at this circuit, this goes into here, and the lowest bit goes into here. So this AND gate actually represents, so basically this first row of AND gates is the combination of all the bits. This one and this one, and the second one here and the first, and the second and the second. That's what these are. And it would be kind of good if they did them in order, but they didn't. So this AND gate represents the 2 low order bits are on. So if this is a 1, then the output will be an odd number. If they're both odd, if the 2 inputs are both odd, this one will be odd. And then after that, it's just different combinations that would make them turn on. So for example, this is a small example, so we can start asking questions like, what would make the highest bit turn on? Can we actually have, with a 2-bit number times a 2-bit number, could it ever multiply to 8? Like what? So you can only have numbers 0 through 3 times 0 through 3. Is there any way to make 2 numbers multiply to 8? Well, if we had 4 times 2, but we can't have a 4, right? And we could have 8 times 1, but there's no way to get an 8 in here. So there really is no way to get an 8. So the only way this bit would ever turn on would be if it multiplied to 9, right? The only way it could multiply to 9 is if all these bits are on. So we would need something that says, so this bit will turn on only if all the bits are on. So we have a row of gates that has every combination of which combination of bits are on. And this one is if the high bit is on and the high bit is on. And then we have other pieces of hardware trying to make this as simple as possible so the layers can calculate the number as quickly as possible. So the shortest paths to the end. Well, we have all the different combinations where the low one here is on and the high is on, and the high here and the low is on, and have every combination fed into here. So actually this wire ends up being, it will only turn on if all the input bits are on. And then the other ones have combinations where 2 are on with 1 off, and so on. You could work through the logic, but the idea is we didn't have to just take whatever numbers here, add it once, and then if this bit is on, add it again. We might be able to do it faster than having a ripple adder run twice. And then if you've got a little bit, so here's a 4-bit inputs, 4-bit number times a 4-bit number, and then it ends up producing as much as an 8-bit number. So now the questions start to get interesting, like if you multiply 2 4-bit numbers that were unsigned, what is the biggest possible result you could get? How many bits could be in the result? So for example, like in this piece of equipment, that would multiply 2 4-bit numbers. Let's say they were unsigned. So here's number A, bit 0, and then number A, bit 3 comes out here. If you took 2 4-bit numbers, what's the biggest they could be? 15, right? 15 if it's unsigned. 15 times 15 is 255, and how many bits would you need that? So that would be like the worst case, the biggest possible number, that we would need 8 bits, right? So if 2 4-bit numbers were multiplied, it could go as big as 8 bits if they're unsigned. Okay, so that's an important side fact when multiplying. Actually, yeah, let me discuss that right now. So if we're going to multiply a 4-bit number times a 4-bit number, let's say on a machine that uses 32-bit addressing. So all numbers are 32 bits. So if you take a number, a 32-bit number and a 32-bit number, and you multiply them together, in the worst case, we could actually generate a 64-bit answer. And we don't have 64 bits to put it in. So actually, if we have a 32-bit number times a 32-bit number and we multiply them, and the result is 33 or more bits, we're actually going to have an overflow error. We're going to say, sorry, the number's too big. So there's certain rules, like at least one of the numbers can only have 16 bits in it, otherwise we'll definitely have an overflow. So we'll take advantage of some of that too when we talk about it. We'll look at some of the appendixes on this talk. Okay, so now, suppose also we wanted to, now we talked earlier in the course, we talked about how to represent floating point numbers. So just a little refresher. Remember the floating point numbers, we would have one bit that says the sign of the number, 0 meaning a positive number, and 1 meaning a negative number. We'd have a certain number of bits that tells us what the exponent is. But if you remember the way the exponents were recorded, they weren't recorded as positive and negative numbers, there was a bias. So whatever number appeared here, we would subtract the number if you had a 0 and the rest were 1. So in other words, if we allow 4 bits for the exponent, whatever number appears here, we subtract 7 from it, and that actually tells us what the exponent is. Remember that? So instead of having like a negative, exponents could be negative or positive, and instead of storing a 2's complement number to represent negatives and positives, we decided whatever number we put in here, we would subtract 7 from it, and that's the actual exponent. So if you have a 9 here, like here's a 9, subtract 7. So this is actually saying the exponent is positive 2. And in this case, it's a 7. That's actually the exponent is 0. So if you want to represent a negative number, you could put, any number less than 7 would represent a negative exponent, and then everything above 7 is how much you are above 0, actually. So that was one of the confusing things when the IEEE decided to represent exponents, which could be positive or negative, by using this bias. Then the other thing you have to remember is that the bits in the fractional part are missing the leading 1. Remember we said All mantisses would start with a 1 in binary, so why record it since we know it's a 1, so we got rid of it. So this is really the part after the decimal. Okay, so that was just a little refresher. If this doesn't make sense, just review that topic again. So if we wanted to record the number 1.01, which is really like the number 5 in binary. 1.01 times 2 to the 2 really means move the decimal over 2 places, so it's 101. It's really the number 5. Right, so this is just the number 5. Does that make sense? That's the number 5. Okay. So how did we do it? Where did this 2 come from? The fact that the exponent is 9. When you take 9 and minus 7, you get a positive 2 as the exponent. And where did this 1.01 come from? We put a 1, the one we took away, put the 1 back, and put the decimal right in here. So it's 1.010. So this is effectively the number 5, represented as a floating point number, positive 5. The next number, we take the fractional part, we put a 1.11. So it's 1.11 times 2 raised to what power? Well, whatever we have as the exponent, we subtract 7. And whatever's left over, that's what the exponent is. So 7 minus 7 is, the exponent is 0. Okay, so what are these numbers? So this is a 5, and this is actually 1, what number would that be? 1 plus a half plus a quarter, 1.75. So that, all right, so if we wanted to now multiply, two floating point numbers, we have to go through these steps. We have to convert from 2's complement to scientific notation. We create the mantissa by putting a 1 in front of the fractional part, to the left of the fraction. Subtract the bias from the exponent, subtract 7 from whatever the exponent is. Then, once we have it in this scientific form, once we convert from 2's complement to scientific notation, we then multiply the mantissas, just like standard multiplying, to get this part. We add the exponents to get what they add up to. Now the question is, in this case, after multiplying this part, we have 10.0011. We want to move the decimal place so it always starts with 1 point something. So by moving the decimal place, we up this to 3. And then we now record the exponent, which is, the exponent would be 3. So we would make that 7 plus 3 is 10. So the exponent is 10, the sign is 0, meaning positive. And the mantissa part would be, so the decimal slid over here, we get rid of the 1, and then we take the most significant bits. The first 3 are 0, so we just record 0, 0, 0. So this is a strange number where the fractional part we're only given 3 bits for it. It's more just to illustrate the form. Okay. So, kind of going through that last example again, we're taking this number. This is the representation for the number positive 5 in floating point. So it's really, again, it's 1.01 times 2 raised to the power of whatever the exponent is minus 7, minus the bias, gives us the exponent of 2. So 1.01 times 2 to the 2 is equal to 5. And then this is the fractional part is 1 point, that's a slightly different number, 1.11, and the exponent again is 7, so we subtract 7 from 7 gives us an exponent of 0. So this fractional part, we put 1 point in front of it, so it's 1.11 times 2 to the 0. So that's another way of saying 1 plus a half plus a quarter, 1.75. So what we're trying to do in this case, by multiplying this number times this number, we're really multiplying 5 times 1.75. So if we multiply those, we get 8.75, and now we have to convert it back to a floating point number. This step, multiplying 5 times this, that would actually be the step where we just showed on the last slide. Multiply this mantissa times this mantissa. Remove the leading one, adjust the exponents, and then copy it back. So we kind of follow, so we're really going along here. We're converting the number to a scientific notation so we can actually do the computation. Multiply this part, add these two together, which would get us to this number, and then we want to convert it back. So we need to, the exponent would be 2. After adding the exponents together, we would adjust it, make it a 3, and now we'd end up with 1.00011. We get rid of the 1 point, and we just record 0, 0, 0. And the exponent is 3, which is 7 plus 3 would be 10. So we end up recording an exponent of 10. Okay. Yeah, so this example is just trying to make it a point. This would be like a silly way to represent numbers. If we had a very small number of bits, this is what we'd end up doing. Now, we'd actually even, it's demonstrating there is a round-off error, because what we recorded, the correct answer, 5 times 1.75 is 8.75, but all we recorded was 8, because we didn't have enough bits to record. It's the closest thing we could record. So we ended up recording 1.000 raised to the third power, which is 8, right? 2 times 2 times 2 is 8. So yeah, we did the math, but we lost some precision. We lost the 0.75 because we just don't have enough bits to represent the number. So more of just an illustration. Okay. All right, so that's kind of the idea behind dividing. You know, we're not gonna design a circuit, but that's the idea of what would go into the circuit. If we were dividing, so dividing in regular, decimal numbers, if we said 4 divided by 21, so I don't know if this is the way you learned it when you were a kid, maybe they teach it differently now, but you would ask yourself, how many 4s go into, you'd now start, so basically you're doing the reverse of multiplying. You're saying how many 4s go into the biggest number, the 2, and there's no 4s in there. So you take another number, you say how many 4s are in 21, and there's 5. All right, so you write a 5. Is that the way you learned it? Okay. I didn't know if that's a new way. All right, so how many 4s are in 21? There's 5. Now you take 5 times 4, and it's because you want to see how much is left over. So 5 times 4 is 20. You subtract 21 minus 20 is 1. And then you can ask yourself, how many 4s are in 1? And there aren't any. So you bring down a 0. Now we'll just put a decimal point and start putting in zeros until this thing goes away, until there's no more remainder. So we bring a 0 down, and now we have 1.0. How many 4s are in 10? There's 2. 2 times 4 is 8. We subtract 10 minus 8 is 2. We ask how many 4s are in 2? There aren't any, so we bring another 0 down. How many 4s are in 20? There's 5. So we put a 5 here. 5 times 4 is 20, and we're done. As soon as you get a remainder of 0, you're done, right? So you keep just trying to keep calculating the decimal until there is no more. So 21 divided by 4 is 5.25, right? So this is, again, just a little review of, remember how old you were when you learned? So like, actually, I think it's around 8 or 9 years old, about that. 6 and 7 years old, you're learning plus and minus, and then 8 years old, you learn divide. No, multiply. You learn divide at 9 years old? You remember how old you were when you learned how to divide? I don't know, somewhere around 9 or 10 years old. All right, so anyway. If you're doing the same thing in binary, there's the same numbers. Here's 4. This is 21. And this is going to end up being 5.25. So it's the same exact computation. So we're asking, but we're going to notice there's not as much thinking. You're just doing bit comparing. We compare these bits to these 4 bits and ask ourselves, is this smaller than this? That means there's one inside, or at least one inside of it. And there can only be one inside because we're using binary. So we write the number of, what we write up here is how many 4s are in 21? 5 of them. Well, we only have binary numbers, so there can only be 1 inside. There's no way to get 2 inside because we would have had it on the previous computation. So if 4 fits in here, we put a 1 here. 101 minus 100 is 1. Now we go to the next one. If this has 2 bits, if a 4 can't fit in there, we put a 0. And if it can fit, we put a 1. So we're just going to check, is one number bigger than the other? So now it would be nice to have a piece of equipment that if you gave it 2 binary numbers, a wire will turn on that says, yes, the one on the left is bigger than the one on the right. It would be nice to have a piece of equipment like that because we're going to use that a lot. So now we're asking ourselves, is 101 greater than or equal to 100? And if the answer is yes, you put a 1 here. If the answer is no, you put a 0 here. And then you subtract. And again, a 1 is left over. So we bring down a 0 and ask ourselves, can this fit inside of here? And the answer is no. We bring down another 0. Can this fit in here? And then we have no remainder. And we're done. So 21, right, this is 21, right? 16 plus 4 plus 1, 0.00. That's a 21. That's a 4. And it divided, it turned into, we're keeping track of the decimal point, 101, which is a 5, and then point. So again, this is not electronic math, this is just in our mind. In electronics, we don't have a decimal. 101 is 5, and then point, the first bit is 50% or not, a half, a quarter, an eighth, a 16th. So this is 5 1/4. Okay, so now, we're doing the same exact steps. So what steps are we doing? The steps that we're doing is, we're asking ourselves, is this number as big as this number? If so, put a 1 here. If not, put a 0 here. So we can design that in hardware. Now, if you want to subtract, so unfortunately we have to do a subtract. You take this number minus this number. And whatever these bits are, we subtract this number. But we know that if you take a number, a positive number, and you write it in 2's complement form, now you have the negative of it. If you add the negative, that's the same as subtracting. So one thing we want to do before we start a division, we want to take this number, the thing we're dividing by, and immediately convert it into a 2's complement version of itself, because we're going to keep subtracting it over and over. And we don't know how to subtract, but we know how to add a negative number. So one of the first things we'll do before we do a divide is convert this into a 2's complement, which is just flip over every bit and then increment it by 1. Then we just keep adding. So every time I say subtract 101 minus 100, I'm actually saying add the 2's complement of this. And then we could just do this computation until we hit a 0, or run out of bits, and then we're done. Okay, so if you're dividing floating point numbers, here's another example. We could take, so again, we'll do the same thing, positive 21 divided by positive 4. So how do we represent positive 4? So positive 4 is 1.00 times 2 to the 2. So we think of that, so we want an exponent of 9, because we're always going to subtract a bias of 7. So to represent a positive 4, you say positive. We know there's a 1 and a decimal that we can't see, so it's 1.000, so we put 4 zeros here, and we make the exponent 9, because like we say, an exponent of 9 is really an exponent of positive 2, because we subtract a bias of 7. If you want to represent 21, 21 is really 10101, so the decimal's all the way over here. So we want really an exponent of 4, right? So basically we represent as 10101, which is like going 1, 2, 3, move the decimal over and make the exponent 4. And then to record this number, the 1 and the decimal gets lost. This is 0101 because there's an imaginary 1 point something here. And then the exponent is 11 because we want an exponent of 4, and we know we're going to subtract 7, so we make it 11. So this is a floating point version of positive 4. This is the floating point version of 21. We're going to do divide. Again, we follow the same steps. Copy the 2's complement into scientific notation. Create the mantisses by putting a 1 to the left of the fraction, so it's a 1.0. Subtract the bias to get the correct exponents. Do the division, so we're really dividing this number by this number, doing the division like we said on the last slide. We're subtracting the exponents instead of adding them, and then make the adjustments and have the result come back. Okay. Okay. All right, so yeah, this is just kind of a quick version of the last slide. So we're basically taking the number 21, converting it into scientific notation, which is really represented by this. So this number divided by this number gives us 5.4, and then we want to convert it back to the correct answer. And in this case, we actually had enough bits to keep the correct answer. The correct answer being 5.25, which is fully represented by this number. So to represent 5.25, it's 101.01. That's 5 1/4. We want to move the decimal 2 places, so we make this a 2, move the decimal over 2, get rid of that. So record this piece, 0101, and record the exponent of, an exponent of 9 means positive 2. Okay. All right, so yeah, so that's kind of just, the talk on just the theory behind multiplying numbers. And then I kind of had a couple of appendixes. So, suppose, for example, I'm using like 4-bit and 2-bit examples just to get the point across. But on a 32-bit machine, and now it's very popular 64-bit machine. But if we had a 32-bit machine, if you're going to multiply a 32-bit number times a 32-bit number, and you're going to use, every time there's a 1, you add, and every time there's a 0, you skip it. How many different adds? And we have to kind of figure out what's the worst case scenario, right? Because we have to set the clock to give enough time to do the multiplication before we start the next instruction. So we have to ask ourselves, what's the worst case scenario? How many successive adds would there have to be? And, right, so what would that be? So suppose you had two 32-bit numbers, and again, let's look at the unsigned, no positive, negative. It doesn't make a difference once we add positives and negatives. But if you had two 32-bit numbers, you were going to multiply them together. How many possible times would you have to do an add? So really, what we're kind of getting at is, here's 4 bits times 4 bits. So we have one layer of results, these AND gates. They feed into a second layer. And then those results, when you're adding numbers together, they feed into a third layer and a fourth layer. So for 4 bits of numbers, there's 1, 2, 3, there's 4 layers of results. And the more layers there are, the more time we have to allow. It would be nice if we could do this concurrently, not have answers feed into the next layer, because then we have to allow more time. So if you notice, we're not adding, the one number we're adding is 4, so at each time we're rippling a new computation, it's not like we're not adding 32 bits to 32 bits to 32 bits. It's whatever the number that we keep adding over and over, however big that is, from the first one until the last digit, however big that is, it's that subset that we keep adding. So it could get smaller and smaller, right? So now the question is, if we're multiplying two 32-bit numbers together, if we're multiplying two 32-bit numbers together, what is the worst case? The most number of times we would have to add a number to itself. Meaning we'll have another layer of hardware that's taking results from a previous layer. What would you say is the worst case? So if you have a number A times a number B, and A is 32 bits and B is 32 bits. So it's really the number of ones in B will cause us to do an add. right? So the worst case, there might be 32. If it's an unsigned number, they could all be ones. But what did we say? If you're multiplying two 32-bit numbers together, if you're multiplying two 32-bit numbers together, and the second number is all ones, yeah, then every time you see a 1, we have to do another add. Is there any way we could maybe somehow do less work? So, all right, so two observations. Number one is an algorithm that came out in the late 50s called Booth's algorithm. Somebody named Booth. There's actually a picture of a machine that does it, and you put the two numbers in, you're multiplying, and you turn the crank, and then it adds the numbers together and slides over one, and you have to like turn it 32 times, and eventually the answer comes out. Then it got put into a computer. But the idea was this: we want to make the worst case as few number of adds as possible. So suppose, for example, it's just kind of an observation. Suppose we had a positive number like 63. Suppose we had an 8-bit machine, and we had a positive number like 63. 63 is represented as 0, 0, 1, 1, 1, 1, 1, 1. Well, if we're going to, every time we see one of these, we have to take the top number, slide it over 1, and add it to the previous result. That's going to be 6 adds. We're going to have to add 6 times. So whoever Booth is made an observation that a number like positive 63 is really like 64 minus 1. And why is he thinking 64? Well, 64 is the number where we have a 1 here and then a bunch of zeros. So that would only require 1 add, but then you have to do 1 subtract at the end to make it come out right. And a subtract, like we said, is really just an add. You're subtracting the 2's complement, right? So if you instead of subtracting by a number like 6, you add negative 6. It's the same as subtracting by 6. So you convert it into 2's complement, you add it. So really, instead of having 6 adds, you have 2 of them. You do an add and a minus. Instead of doing 63 times a number, you do 64 times the number and subtract 1 times the number, which is the same as 63 times the number. But to do a 64 is a lot less work than a 63. A 64 requires copying the number 1. Slide it over 6 places and you're done. This means add it 6 times to itself. That'll take a lot of time. Okay, so the number 63 would require us to shift and add 6 times. But if we did it by 64, multiplying by 64 means just add it to itself once and then do 1 subtract at the end. So it's 2 operations versus 6 operations. So the idea is to kind of like play around, realizing that the 1s caused us to do work and the 0s caused us to do no work. Let's try to change the number so there's a lot of zeros. Okay, so, well, so it's not like every time you're reading a number, the first time you see a 1, it's not 1s the rest of the way. But, so for example, the number 63 could be represented like this, but that's really 64 minus 1. The number 7 could be represented like this, but that's really 8 minus 1. So we're starting to think of all the numbers as powers of 2 minus 1. And seeing how much this could help us. So suppose you had a number like 56. Isn't 56 really 63 minus 7? So it's like a 63 minus 7. So this is really 56. So, all right, so here's what we're doing. We're taking numbers and saying, reading from left to right, every time you switch from a 0 to a 1, like Booth's algorithm, if you read the write-up on like Wikipedia, it says every time you see a 0 and a 1, flip it and make it a 1 and a 0. So turn this into 64 minus 1, and then continue reading until you see a 1 followed by a 0 and flip those and turn that into 8 minus 1. So really what they're saying to do is, if a number is like 56, think of it, isn't 56 really 63 minus 7, and 63 is really 64 minus 1, minus 8 minus 7. So isn't it really 64 minus 8? Right? So yeah, like I say, this is something you might want to look at 2 or 3 times before it just kind of clicks what's happening. But a number like 56, which only actually has 3 ones in it. So actually, if we just multiply by 56, we would do 3 adds and we're finished. But you could think of the number 56 as really 64 minus 8. So we can multiply it by 64, then multiply the number by 8, and then subtract 64 by 8, so we could save 1 additional add. All right, so the logic behind Booth's algorithm is if you're multiplying by a number that has a lot of ones, we could think of that number as an adding and subtracting of numbers that are much easier to use, and we might be able to save some steps. So, so that could help us. So now here's a second appendix. If we were multiplying 2 numbers, let's say, and we talked about this a little bit earlier, suppose we multiply 2 8-bit numbers. Here's an 8-bit number and an 8-bit number. What would have to happen for us to have an overflow? For us to have an overflow, if one of the numbers had a 1 in the upper half, I'm sorry, if both numbers had at least a 1 in the upper half, we're going to have an overflow. These are the smallest possible numbers where there's a 1 in the upper half of the number, right? So this number times this number will have an overflow. So we can actually, before we even do any multiplying, we could check, is there at least a 1 here and a 1 here? If so, there's no point even doing it because the numbers are too big. So we can have a piece of hardware that says, take all these bits, and if one of them is on, take all these bits and one of them is on, and if both of those are on, just say forget it, overflow. Don't even do the math. So that tells us right away, the only time we'll ever even do the math, at least one number, the whole upper half has to be all zeros. At least one number meets that condition, right? If neither number met it, we can't even do the math. So one number, the upper half of all its digits must be 0. This is again on the positive side. The same argument goes on the negative side. So why don't we use that number as the one we do the repetitive adds on? So we know half the bits are going to be 0 for at least one of our numbers. The lower half could be a mixture of zeros and ones, right? So what's the worst case? Every time there's a 1, we have to do another shift and add, shift, add. So what's the worst case? So if you had a number, if you had an n-bit number, let's say you're on a 32-bit machine. So the second number you're multiplying by, we know the last 16 bits have to be 0, otherwise it's not even worth multiplying. So the first 16 bits could be a mixture of zeros and ones. What's the worst case? Every time there's a 1, we have to do another add. So what number will give us the most work? It would be if the first 16 bits are 1s. Worst case scenario on a 32-bit numbers, we may have to do a shift add 16 times. But according to Booth's algorithm, we can turn 16 into 2, right? So now what we can kind of do is we can kind of combine this idea with Booth's algorithm and say, if we have a lot of 1s, maybe we could start reducing the number of 1s by converting it into the Booth's algorithm equivalent, which has a lot of zeros. So it makes the number of adds even smaller than half the number. So for a 32-bit number, you might think, worst case scenario, I have to do 16 adds. But with Booth's algorithm, we can make it even smaller and smaller. It comes down to about 5/16 of the number of bits. So if you have 32 bits, the worst case scenario is you're going to only have to do 10 adds before you're done. And then, so we could build a circuit that would be a lot smaller than what originally meets the eye. So, okay, yeah. So the worst case scenario of how many shifts and adds would be if you have n bits, half of them, one number, half of them is going to be all zeros in the upper half. Otherwise, we can't do the math. And once that's the truth, then what's the worst case for the lowest set of bits? It's not n over 2. It's going to be, using Booth's algorithm, we could make it almost half that. A little bit more than half of that would be the number of times we would have to design the hardware to do the shift. So we're really, if you want to, the way they designed a lot of processors in the 80s was to use Booth's algorithm and not Booth's algorithm, and have something read the number to say which of the two would be faster, and always have the two results come out and feed them into one answer. And whichever one is faster, take that one, take that answer. And you'd have to only allow enough time for whichever is the quicker of the two. Because one of them, they'll both compute this correct answer. Based on the number of ones, and the lower half of the number would determine which one could calculate it faster. And then you only have to allow the clock enough time to get either answer to come out, because we'll have the correct answer. Okay.